Hello students, myself Shamrat Paul. I am going to introduce the topic on single phase full bridge inverter with R and RL load. So first go to the circuit diagram. This is the circuit diagram of the full bridge inverter with RL load. With R load, sorry. And as it is a full bridge inverter, that is why we are using a bridge circuit over here, in which we are using the 4 switches S1, S2, S3, S4, and we are applying the constant DC supply or DC link voltage is having magnitude Vs, and only R load is there. In this case, diode D1, D2, D3 and D4 may not be conducted. Whenever we are going through the circuit for application for the RL load, then diode D1, D2, D3, D4 will be conducted. So here we are explaining the working by two mode operation, mode 1 and mode 2 operation. Okay, in mode 1 operation, see, when S1 and S2 starts conducting, then the current starts flowing through S1 through load, then S2, then coming back to the supply. It will cover the mode 1 operation, and the circuit diagram is given over here. Similarly, when S1 stops working, then we are giving the triggering pulse next two switches, that is S3 and S4. Then the current starts flowing from S3 to load, then S4 and coming back to the supply, which will be reflected on the next circuit in mode 2 operation. Okay, so that means, and this duration of the conduction we can consider by the two half, 0 to T by 2 and next operation T by 2 to T, as it will provide the periodic signal. That is why we are applying the triggering pulse 0 to T first for mode operation, that is 0 to T by 2, and for the next mode operation T by 2 to T. Okay, and the first mode operation S1 S2 is on, in the next mode operation S3 S4 on, and this is the equivalent circuit diagram is given over here. Now see, by considering this two mode operation, we can form the waveforms output voltage and output current. When S1 S2 starts conducting, then current is flowing through this path. In this case, the polarity of the output voltage is, this is positive and this one is negative. Your left hand side is positive and right hand side is negative, and current is flowing from your left hand side to right hand side across the load. Assume this is the reference polarity and reference direction of the current, and assume it is a positive. That is why in the first mode operation, during this duration, the output voltage is this one. In the next mode operation, then the S1 and S2 stops conducting and S3 and S4 becomes on, then the direction of the current is given in this circuit. Now see, right now the polarity of the voltage is opposite with respect to the previous one, as well as the direction of the current is opposite with respect to previous one. That is why we can say across the voltage, the polarity of the voltage and the current is opposite direction. That is why during T2 to T, the direction of the voltage and current is opposite. As we are using only the resistive load, that is why voltage and current both will be in same phase. That is why the output current waveform, which will follow the output voltage waveform, and which is having the magnitude of Vs by R, as Vs is the output magnitude voltage. As we are giving the supply voltage is Vs, that will appear across load, that is Vs. Okay. Now we are going to express by mathematical expression in terms of RMS voltage and in terms of periodic signal using the Fourier series. So first calculate the RMS voltage. See, RMS voltage means root mean square of the output magnitude, output voltage magnitude, right? Similarly, we will do it here. Now see, this is the expression for the output voltage magnitude defined by the RMS value. That means we can say the RMS value root mean square, that is why V0 square, V0t square, right, and under root. And we have taken the limit, that is 0 to t by 2 for first half cycle or positive cycle, and the time duration is t by 2. That is why the expression will be 1 by t by 2, 0 to t by 2, V0 tt dt under root. That means after simplification we can have, this is the result, as the output voltage that will similar to the input voltage, we can replace the term by Vs, okay, and further integrating this part, that is Vs square, so we will get this result 2 by t Vs square t by 2 under root. So the expression of the RMS value equal to Vs just is similar to input voltage Vs. That means input voltage and the RMS voltage both are same in magnitude. Now deduce the expression of the by periodic function that is taken from the Fourier series. So we know the expression of the Fourier series which is defined by the, which will be defined the periodic function, that is V0t equal to summation of n equal to 1, 3, 5 to infinity. We are considering the odd harmonics as the output voltage is, half wave symmetrical. See, the output voltage is this one, right? That means we can say this first half and the next half is similar to each other, and similarly this is similar to each other. That means we can see for a complete cycle T, it will provide you the symmetrical waveform or half wave symmetry. That is why, as we know, in case of the half wave symmetry, A0 and the coefficient A1, which will give you the magnitude is 0, and which will be replaced by only the coefficient Bn. That is why this is defined by Bn. So expression is 2 by pi integrating of 0 to pi V0t sin n omega t d omega t. After simplification, we will get the result, that is sin n omega t d omega t, and we know the integration of the sin omega t, which will give you the minus cos omega t. That is why replaced by this term minus cos omega t, and n is defined by 1 by n for integrating part. That is why we will get the result, this one. And after considering the value lower limit 0 and upper limit pi, then we will have the value, that is cos 0 minus cos n pi, as it is half wave symmetrical. That is why we should consider the n should be odd number. That is why if we can put the n equal to 1, 3, 5, all the cases, the cos n, cos 3 pi, cos 5 pi, which will give you minus 1. That is why the expression that is defined by 2 Vs by n pi 1 minus of minus 1, that will give you 2, and multiplied by 2, that is give you 4. So this is the coefficient defined by this expression Bn equal to 4 Vs by n pi. See, in the previous section, when we calculated the part of coefficient Bn in case of the half bridge inverter, then we had got the result, then it was Bn equal to 2 Vs by n pi. That means what? In this case, we are having the double value with respect to the previous one. That is why this type of full bridge rectifier, which will give you the maximum output voltage with respect to input. Okay, That is a good advantage or the merits of using this kind of circuit. So ultimately, by putting the value of Bn from this one to the actual periodic equation, so it will give you the V0t equal to n equal to 1352 infinity 4 Vs by n pi sine n omega t. So as we are using the resistive load, that is why voltage and current both will be in the same phase. That is why the output current expression will be, that is Vs by R, that means 4 Vs by n pi R sine omega t. So this is the output expression. So this is all about for the implementation of the R load. Now we can go through by using the RL load. So what will be the changes during the operation? In case of the R load, I have mentioned there is a no conducting state was mentioned during D1, D2, D3 and D4. But in this case, as we are using the RL load, then the question for the charging and discharging path. That is why this charging and discharging part should be maintained by using this diode. Now see, all the cases when the diode starts conducting, then the stored energy inside the inductor, which will be feedbacked from load to source. That is why this kind of diode is called feedback diode, as it is eligible to feedback in energy of the load to the supply. That is why this is called feedback diode. Now it had been well described by the 4-mode operation as the inductor is there. Okay, so in this case, see, when the switch but we have to concern about it. The switch S1, S2 can be conducted at any instant, and for the next cycle S3, S4 will be conducted, but never try to giving the triggering pulse across S1, S4 or S3 and S2, because it will give you the short circuit path. It will provide the short circuit path and the thyristor will be damaged permanently. So to avoid this short circuit path, we never can be applying the triggering pulse, the similar switch which is connected in the same leg. Okay, so first now go to the operation. Suppose when the switch S1 and S2 starts conducting during the cycle T1 to T by 2, then the current starts flowing through this direction and it's coming back to the supply, right? Then the inductor will charge. This will be positive, this will be negative. And when the inductor try to discharge for the next mode operation or the next duration, then it has changed its polarity. Then inductor try to discharge through the diode D3 to supply, then D4 and coming back to the load. That means it is eligible to feedback energy from stored inside the load to the supply. That is why the diode is called the feedback diode. So in this way we can consider the other modes operation, which is reflected in these diagrams. That is for mode 1, mode 2 and mode 3 operation, and duration is given, suppose T1 to T2, T by 2. The next mode, that is, will start from T2 to next T2. Again next mode will start from T2, then T2 to T, capital T, and next will be start from T2. Next the triggering pulse is given to the S12. Okay, so by considering this mode operation, see, when the current starts flowing in this direction and the voltage, the polarity of the voltage is appearing across the load is in this way, then the output voltage is this one is positive. Okay, when S1, S2 starts conducting. And on the next case, when the S2, S3 starts conducting, means in this case, then see, with respect to the current direction, now is opposite direction, as well as the voltage appearing across the first load and this appearing load is reversed in polarity. That is why when the S3, S4 starts conducting, it will provide the reverse voltage across the load or negative voltage across the load. Now consider the output current. See, so during first mode operation, T1 to T by 2 means this mode operation, T1 by T by 2. What happened? Then when the current starts flowing in this direction, the inductor gets charged. Inductor starts storing energy. Then the current will be gradually increases. That is why the current is gradually increases. After first mode operation, when the second mode operation starts, then this stored energy try to discharge through the diode. That means what? That means then the current starts discharging from its high value to low value in this mode of operation. When the mode 3 becomes, then what happened? Again the current starts flowing through this direction. That means again the inductor starts storing energy but in opposite direction with respect to the first mode operation. That is why inductor starts storing energy and the current is gradually increases in negative direction during this operation. Okay, and the inductor again try to discharge, which is followed by this equation in this circuit. Then the negative stored high energy or current try to discharge right now during this mode operation until we are giving the next triggering pulse to the switch. That is why this is the waveform. That means it will be continue for the next cycle onward just through this manner. Okay, so this is the operation and the waveforms of the full inverter circuit. Now, what will be the periodic expression and RMS value? Just we have calculated in the case of the R load. That is why the RMS value is always which will provide you Vs, right? That means, and the Vs and the periodic function of the output voltage that is defined by in the previous class in the R load application, that was 4 Vs by N pi. Right, but here we are using, as we are using the inductive load, then the output current expression will change. Okay, as the load has changed. Previously it was in resistive load and right now it is inductive load. That is the current expression, that is 4 Vs by N pi under root R square plus N omega L square sine N omega t minus phi. As the inductive property is there, that is why current always lags behind the voltage. That is why, which is defined by minus phi n. And as we are using the inductive load, that is which should be replaced by the impedance part Z, which is having the value R square plus N omega L whole square. That is the final expression for the output current during RL operation. Okay, thank you.